Alright, so hi everyone. I hope you guys are following well with the lecture on probability. So we are going to continue our discussion on probability, and today we're going to something new. I guess from the previous section, so far we discussed what probability is, and we talked about Venn diagram and those things you might be familiar with. But today we're going to learn about Bayes' theorem and condition of probability. So you might or might not have dealt with this kind of probability, but this is going to be serve as another fundamental concept in probability, right? And there are some interesting things here. So let's just get started. Right. So let's talk about condition of probability. Okay, so condition of probability, as the title suggests, this is probability conditioned upon something else. Okay, so we call this, in notation we write it down as condition of probability of a given B, right? So this is probability of a event A occurring given B. Alright, so what it's saying is that we're looking at a particular event A given that B has happened already. Okay, so it might not be really clear, so let's just before we illustrate this, we are going to write down the formula here. So this is as follows. This is probability of A and B happening over probability of B. Okay, so let's look at a simple example. Just say that where we roll the die. Actually, we say that we rolled 2 dice, so roll 2 dice. Okay, and what is the sum? What's the probability the sum of the 2 dice are even? So probability that 2 sum of 2 dice is even number. Okay, this is the first part, and we're going to look at another. This is the part A. That's going to be the review for what we discussed. So roll the 2 dice. Probability that the sum of 2 dice is even, given, so these the same, given that at least one of the dice is a 6. Okay, so roll the dice, probability that sum of the 2 dice is even number. So this is going to be just a regular probability question. So why don't we lay out all the possibilities here? Okay. So say, later on we're not going to do this, but this is our first time, so we're just going to write down every possibility. So right here it's 1 1, say 2 1, 3 1, 4 1, oops, 4 1, 5 1, 6 1. Okay. 2 1 2 2, 3 2 4. This is 2 1. 5 2, sorry, 6 2 3 1 4 1 5 1 6 1. Okay, so 2 3, oops, 3 3 3 3 5 3. Okay, so this is a little confusing, but let's look at this. Probably the sum of two dice is even, right? So even numbers are this, 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 right? This is 3 4 5 6 7 8 4 6 8 6 8 10 6 8 10 8 10 and 12, right? So if you count these up, this is going to be actually half, right? But now moving on to B, we're looking at the probability. Given probability that the sum is even number, given that one of the dice is a 6. Okay? Right, so one of the dice is 6. Let's just, we're not going, here, from here, we're not going to look at every single case. So here, the sample size, the sample, space decreases because one of the dice has to be 1. So let's just color them off. One of the dice has to be 6. So we have here, okay, and these right here. Okay, so if we count them off, how many options do we have in total? So this is 5 and 6, so that's going to be out of 11. Right, so out of 11. And we want even and with the 6, so even, so the yellow. Within the blue, we're looking for the yellow, right? So 1 2 3 4 5. So the answer is this. But so just remember what we did. For the top part, we're looking at the intersection between even number and one of the dice being a 6. That's the top part. And the bottom part is a sample space, which means that at least one of the dice has to be a 6. So that's how we came up with this 11. Alright? Okay, so why don't we look at another example? Okay, so this is another example. So this is going to show us a graph. This is underweight, healthy weight, overweight, and obese. We're talking about the weight and CAM, no CEM. I'm going to explain in a minute what it means. And we have, right? The CAM stands for Complementary Alternative Medicine. This includes acupuncture, yoga, massage, right? So all these stuff included, right? So we're looking at the information of two tables, right? concerning the use of CAM in the past year and the weight class based on the body mass index. So we're just going to, okay, it's just, okay, so it just came up again, and we're going to look at this with the proportion or a probability. Clear this up a little. Alright, so I'm going to assign some probabilities here. So pretty much we're looking at the effectiveness of this therapy, CAM, and let's see how that works out. So these are the totals. So I saw that 32 and 62 and here it's 1. Okay, so this is a table that you're going to base off of, and I'll give you some questions to work on, right? So I want you to pause the video and work on these questions. So what is the probability that a person selected at random from this population will have used CAM in the past year? Okay, that's part A. Part B is a okay, so a person is found to be overweight. What is the probability that this person used CAM in the last year? Okay, so work on this problem. It might be a little confusing at first, but just try your best and give it a shot and come back to it when you're ready. Okay, so pause the video and work on it. Alright, so I hope you all worked on it, or try to read the question and see what's going on. So here is the chart. Okay, so basically what it's saying is that this is from the data from last year, and if you use this therapy method, CAM, then these are the percentages, and we have no CAM, and these are here are the probabilities here. And so we're looking at the probability that a person selected at random from this population will have used CAM in the past year. Okay, so we're looking at a person selected at random, so we're definitely using this probability from this population will have used CAM. Right, so what's the total for CAM? The population who with the usage of CAM, total is right here, 32. Okay, so that's going to be 0.32, because if you add these up, 1, 2, 3, 4, these are the subcategories of CAM. Right? So if you were to draw a Venn diagram, I'm not sure if it's a good example to draw a Venn diagram, but I think it's going to make some points here. So here is CAM, and there's no CAM, And obviously these two events are mutually exclusive because we cannot have CAM and no CAM at the same time. And within CAM we have, okay, so within CAM we have underweight, healthy weight, overweight, and obese. Okay? And same for no CM. So we have underweight, heavy, overweight, and obese. So this is how it looks like, and we're looking for the population who have used CAM in the past year. So it's going to be just um, these, right? And the total says 32 right here, and that's the number we use. And it says a person is found to be overweight. So we're only looking at the overweight population. And what is the probability that this person used CAM in the last year, right? So if you were to assign some events here, let's say O equals being overweight, C equals use CAM in the last year, right? So what is this probability? We're looking at probability that a person used CAM, so that's going to be probability of C, given that the person is overweight. So given that the person is overweight, right? Because that person is already found to be overweight. So among the overweight population, how uh, how likely is it to have used CAM? So that's CAM given O, right? So, and we've discussed this before. This is probability of C and O together over probability of O. Okay, so let's look at this. Probability of C and O. So have used CAM and is overweight. So this is the number that we're going to use. Right, so that's 0.12 out of probability of overweight. So we're looking at probability overweight right here. That's going to be, I can't seem to find my, okay, here, 33. So that's 0.33. So this is the answer. Okay, so that's basically how we use conditional probability. When we're restricting the sample size, that's how it seems to be. Right. So let's now look at another definition. Here we established that just reviewing what we talked about before. This is the formula given, right? And if you were to multiply these two, what do we get? So P A and B equals P of B times P of A given B. Okay? So this is called the multiplication law of probability. Okay? Um, so it's saying that if you multiply the probability of B and probability of A given B, then you're going to end up with the A intersects B. Okay? Alright, so let's look at another example showing this. And here we have the second example. Alright, so two cards are drawn from a deck without replacement. And what is the probability that the first card is a king and the second card is a king as well? Alright, so let's first assign some events. Say that K1 is first card is a king. Okay, and K2 is second card is a king. Okay, so probability that the first card is a king and the second card is a king is a probability that K1, K2. Right, using this formula here, we can see that this is probability of K2 times probability that K1 given K2. Oops. I'm not sure what it's doing. And I forgot to mention here that here this can also be the case. If this is the case, we can also say that this is probability of A times probability of B given A. So here you have to be a little careful with this, because sometimes you might want to use probability of A. You might have probability of A first and then probability of B given A. Okay, so that's something that you need to be careful. And in this case, actually, it's easier for you to do it this way. Probability of K1, and then you would do probability of K2 given K1. Why? Because K2 is conditioned upon K1, right? And here is the keyword here is without replacement. Where's my pen? Okay, without replacement. Right? What it means is that if you draw one card, we're never going to replace it with another card. So if you draw one card, n will become 51. First, this is the first round, n is 52. In the second round, n is going to be 52. So this is without replacement, and this is a series. This is going through a times, not a time, but just a series. It's a sequence, right? So you would do that. So let's look at this. So first, what is the probability of getting a king as a first card? Right, so there are 4 kings in total. In the first round, we have 52 cards, right? And times probability of K2 given K1. Right, so given that we already chose a king as a first card, what's the probability that we're going to have a second king? Right, this is a without replacement question, so it's going to be out of 51 because we already chose one of the card. Right, and how many kings are there left after choosing the first as a king? There are only 3 left. Right, so that's going to be a 3. So if you calculate this, this is 12. Well, we can cancel this out here, so it's going to be 3, 26 and 51, so that's going to be 6, 6, 3, right? So this is the answer. So this is where you would use this formula right here. Let me just highlight this. Okay, so especially for sequence of events. So for a sequence of events like this, where one event is contingent upon the other one, we would want to use this formula. But this is a formal way of writing this, but we already have this in our mind. Whenever we're thinking about probability questions, we already have this in our mind, right? So okay, let's look at another one. Alright, so let's do this. Oops, let's doing this again. Alright, I'll try this. Ooh. Let me erase this first, and then let's move on to another example. Oh no, I've seen this. Okay, so moving on. Let's just look at another example. Alright, so here I wrote down the question for you, the example. There are 25 pens in a container on your desk. Among them, 20 will write well, but 5 have defective ink cartridges. So you will select 2 pens to take to an appointment and calculate the probability that A, both pens are defective, B, one pen is defective but the other will write well. Right, so this is an example for you to try. So take a moment and pause the video and work on it. And once you're done, please come back to it. Alright, so let's talk about this. Right, so it says there are 25 pens and 20 will write well and 5 will be defective. So why don't we just assign some events before we start as usual. So let's say that D is product being defective, and say G is it's a good pen, it writes well. Alright, so and we are going to use subscripts to denote that the order of selection. So for example, if we say D1, G2, that means the first is defective and second is good. Alright, so these are the events that we're going to use. And for the first part, both pens are defective, so that means we're looking for probability of D1, D2. So both of them are defective. And we're going to use the probability conditional probability formula, so this is going to be D1 times D2 given D1. Alright? So in order to calculate the probability of D1, we do have the numbers here, but we didn't calculate the probability. So what is the probability of getting a defective defective pen? That's going to be, so we have five defective, and out of 5, this is right here, 5 defective, and out of 5 there are 25 pens in total. So this is going to be the probability of first being defective, right? And the second is we're choosing, after this is done, given that the first was defective, what's the probability of the second one being defective as well, right? So and that we would write it as, well, we chose one already, so this is going to be out of 24, and we're using the second one, and that's going to be defective, and we already chose the first defective one, so there are 4 left. So this is the probability, and if we cancel this out, it's going to be what is this? This is going to be 1 over 30. Yes, 1 over 30. So this is the answer for part A. Alright, so here is moving on to part B. One pen is defective and the other will write well. Here we have to think about 2 different cases. So first case is when the first is good, but the second one is defective. Okay, and the second case is when first is defective and second one is good. So if we were to write this in terms of probability notations, this is going to be probability of first being good, so G1, D1, D2, sorry, G1, D2, that's the first case, plus the second case is probability of D1, sorry, and G2. So these are the two separate probabilities that we have to look into. Okay, let's look at this. So this part, we can write this as probability of G1 and probability of D2. Given G1, I'm just using the formula here. Probability of D1 times probability of G2 given D1. Okay, so these are two separate probabilities. And let's look at this. Probability of G1. So there are 20 of those, 20 of good ones out of 25 times, if we selected the good one on the first trial, we're going to have 24 left. And how many defective ones are left? Well, there are 5 of them, so this is the probability. Plus, first we're going to choose the defective one, so that's 5 out of 25. And again, if you choose the defective one, we're going to have 24 in total, but the good ones we have 20 left. So this is the probability. All right, so these are what is this, 4, 6, so these are all 1/6. So if you add them up, we're going to get 1/3. Right, so this is an example of conditional probability and using the notation for it. Alright, so we're going to move on to the discussion of independence. We talked about it briefly before. Okay, so independence. So last class we established that two events, right? Two events A and B are independent, called independent when A and B equals A times B. So this is if independent. Okay, and we are going to see this again. So say that if we have A given B, so this is going to be again A and B over probability of B. Okay, and if we're looking at probability of B given A, this is probability of A and B over probability of A. So since we're looking at these, this is condition where if A and B are independent, right? A and B equals A times B, right? Probability of A times probability of B over probability of B. So this is going to be simply probability of A. And same thing here. This is probability of A and probability of B divided by probability of A. This is probability of B. So if these two variables are independent, the conclusion is as follows. So probability of A given B is always probability of A, and probability of B given A is probability of B. And this makes sense if you think about it logically. When we are claiming independence, those two variables are not dependent. So we don't care if it's conditional probability because these two are independent. So given that B has occurred, we don't really care what A is. given that circumstances. So it's not dependent on the result of B. It's just the same as probability of A. So that's independence. All right, so so let's look at another example. Okay, let me write down the example for you. Okay, so here is an example for you to work on. So let me just read it to you first. Engineers use the term reliability as an alternative name for the probability that a device does not fail. Okay? Suppose a mechanical system consists of two components that function independently. Right? So the keyword here is independent. Okay? From expensive, no, not expensive, but extensive system that it is known that component 1 has a reliability of 0.98 and the component 2 has reliability of 95. If the system can function only if both components function, what is the reliability of the system? So only if both components function, and where is it? The keyword here is independent. Okay, so if one of the system fails, then the whole system fails, and we're trying to figure out the reliability of the whole system. So try to work on this. Pause the video right now, and come back to it when you are done. All right? So do that right now. All right. So this is a little bit more complicated system than not system. Sorry, the example that we just did. But let's first assign some events, because that's what we do always. So let's say that A1 equals when component 1 functions. Alright, so this is A1. And say that A2 is when component 2 functions. Right? And we're going to assign another event S. This is when the system functions, the whole system. And the system only functions when? The system functions when A1 and A2, when both are true, when both systems work together, right? Alright, so and here we have the key word independence. So when they operate, each system operates independently, then these two are independent as well. Right, these two are independent. Okay, and now if we're looking at this probability of system, and this is just going to be probability of A1 times probability of A2, because these two are independent, right? And we are already given the probability of A1 and A2. A1 has a reliability of 0.98 and A2 has 0.95. So if you multiply this out, you get 0.931. Right? So the system reliability is 0.931. This is actually not the type of question that I expected. I thought it was going to be more complicated, but apparently it wasn't that complicated. Right? So we're going to move on to another topic, okay, which is very similar to what we just discussed. Okay, this is called the Bayes theorem, and this is used very, very often in probability. Bayes theorem. Okay, so let's look at this. So let me just, before doing anything, let me just draw a Venn diagram to better illustrate this problem, or this theorem rather. So see that this is the sample space, and we have different sections here. Okay. So say that this is B1, B2, B3, B4, and B5. And we have some kind of event going on right here. Say this is the event A. Right? So, sample space of event A. The space of event A is divided by 5 different sections, B1 through B5. Right? So their union, so we will say the sample space of where's my pen? So A is consisted of B1 union B2 union B3 union B4 union and B5, right? And we call these little sections here, so if you have these little sections, we call this partition because we divided them up into different parts, right? So Bayes' theorem states that the rule of probability, doing this again, is as follows. Okay, so say if we have probability of A, okay, this is going to be probability of A and B1, so this part, plus probability of A and B2, so this part, plus dot dot dot, plus probability of A and B5. Okay, so this graphically makes sense because we're just partitioning them and we're adding all the possible partitions. So this would be that, and this would be here. Okay, so this is exactly the Bayes theorem that we're going to use. Alright, and there can be 2 different partitions or 10 different partitions. That's really up to the question or the problem that you're looking at. I don't know why it's doing this again. Okay, we're back. So we're going to look at an example to better illustrate this. Okay, so say that there is so hopefully it will work now. So the example that we're trying to look at is, alright, so suppose that a class is only, I don't know, I'd say that statistics class is only taught by 2 professors. Okay? Say Professor X and Y. And a student is picked at a random, is likely to get Professor, okay, let me just write this down. So the probability that a student selected at random is twice as likely to get Professor X to Y. Alright? And Professor, let's look at this. This is interesting. Professor X passes 80% of his students, and Professor Y passes 70% of the students. Okay, so now we're looking at what is the probability that a student selected at random passes the course. Okay, so give it a moment to think about this problem. So there are different stuff going on, and we just need to be careful with this. So just think about it, pause the video, and try if you can solve this problem and come back to it. All right? Okay. So I hope that you've worked on this, and let's just discuss this. All right. So let's assign some events. Let's say that event A is a student. It's an event that a student passes the course. Okay, and let's assign B1 as the event when the class is taught by Professor X, and B2 is when Professor Y teaches the course. Okay, so since we have the events assigned, let's now look at the problem. So it's asking for the probability when a student passes a course. And how can a student pass a course? Well, there are two options. So option one, or two cases. So the first case is when the student has Professor X. And the second case is when the student has Professor Y. So we need to look at two different cases and add them up. This is where the Bayes theorem comes into play, right? So this is how you would write it down, right? So this is probability of event A occurring, which is probability that a student selected at random passes a course. This is when probability of B1 and probability of A given that B1 happens. So which means that probability, we're multiplying by probability of a student having the Professor X, and then given that the student has that professor, given that the student has Professor X, the student passes the course, right? So that's probability of A given B, plus same thing, probability of B2, so probability of student having Professor Y times probability that student will pass this course given that he has Professor Y. Okay, so this is the Bayes theorem and how we use it, because we have, if you're looking at the Venn diagram here, here is B1 and here is B2, and we're looking for A. So we're adding these up, right? So we're looking for this part. This part is right here where we talk about B1 times A given B1. This is actually, if you're writing this out as a simple notation, this is A and B1. Okay, and here this part is B2 and A. Right, the order doesn't matter because this is an intersection. So this is what this corresponds to. Okay. All right, so let's further discuss this. Alright, so let's look at this. What is the probability of a student having Professor Y, which is probability of B1? It says probability the student at a random is twice as likely to have Professor X to Y. Alright, so what's the probability of getting B1? So it's twice as likely as Y, and they both have to add up to 1. So this is going to be 2/3. Where's my mouse? Okay, here. So this is going to be 2/3 because B1, so side note here, so B1, probability of B1 is twice as likely, so this is twice as the probability of B2, and we have to divide this into 3 parts, equal parts, so this is P of B1 is going to be 2/3, and this is P of B2 is going to be 1/3, right? So that's taken care of. So what is the probability of student passing given that the student has Professor X? It says the Professor X passes 80% of the time, so that's going to be 0.8. Right? And looking at probability of B2 we already established that it's 1/3. And probability of a given B2, which is probability of student passing, given that the student has Professor Y, that's right here, 0.7. So this is going to be 0.7, right? So if you sum this up, you get 0.767. So this is the answer. So that's pretty much how we use Bayes' theorem. Alright, okay. So that's the discussion of Bayes' theorem. I will see that's pretty much all I wanted to cover for today. And I'll give you some examples to work on, and I will go over those as well, right? So look for the class activity worksheet, and we will come back to it.